All right, it's time, so let's get started. We are still studying learning theory, right? How much we can learn after we train a model. If that model is really useful. After we have learned a model from the data, is that model going to be useful for data that we have not seen after training, or during training? So we have already seen the case of classification. Right? In classification, we saw that there is a trade-off between the E-in, the training error, and the generalization error. Right? And that you have to choose the right model for your learning to hit the right balance between training error and generalization error. Right? That's for classification, and we've done that through the Hoeffding inequality and the Hoeffding bound. And then we talked about VC dimension. But for regression, we started earlier this week, and we saw that for regression we don't have Bernoulli random variables anymore, so we cannot really just simply use the Hoeffding bound and the VC dimension. So we have to use what's called the bias variance trade-off. Yeah? And how do we define that? And this is a recap of where we are at so far. First of all, we recognize that the final hypothesis that we choose after training depends on the training data set that we have, obviously, right? And the training data set, the data points are chosen at random, right? So the training data set itself is a random quantity. So therefore, our final hypothesis is also a random quantity. Yeah? So we denote it by G of D, like that. Since it's a random quantity, depending on what kind of training data you have, we can take the mean value, the expected value of this random final hypothesis. Yeah? So G bar is the average of the final hypothesis. Right? The average is a statistical average over what kind of training data points we will get. Right? So that's an expectation taken over the training data points. Yeah? Now, so we define two quantities, bias and variance. What is the bias? Well, bias is simply the distance of this average final hypothesis, or the best hypothesis that you can get out of training. The average of that, the distance of this average from the true target and unknown target function f. The variance is simply the variance of this random quantity, yeah, the random quantity with respect to its own mean value, right? So how random this final hypothesis can be, and then on average, how good is this final hypothesis in terms of the distance from the true target function, right? That's that bias and variance. And we saw an example last time, which was rushing a bit, but the example saw that the test error is actually can be written as a sum of the bias and variance, right? So let's formalize this a bit. Let's first define the test error, because this thing is a bit, it's average, it's a random quantity, right? So we have to define the average out of sample error, or the test error, of course, was for any given sample point. Is that this is important, yeah, for a given sample point. Let's call it E, right? Just corresponds to the error for the sample point that we have seen before. So it has to be an expectation over the training that we get, right? Because this depends on our training result. Yeah, so again, it's a square error. Of course, your predicted label, right, minus the true label, right? Yeah. So that's our clearly we define this as our test error, right? The only new things here is that we have to take the expectation over D, because again, this hypothesis, this estimate depends on the training data points that we get to obtain this final hypothesis, right? Okay. So as we alluded to earlier, previously in the example, this E of x, this average out of sample error, turns out to be equal to the bias plus variance. Yeah? We saw from the example, but can we prove this? Yeah, in general, this is true. Yeah? So what is E of x? Well, it is expectation of that. So notice, what's the difference between this E of x and the bias invariance? Well, you see that E of x is a GD minus F, right? The bias is there's G bar minus F, and then there's GD minus G bar. Right? G bar is kind of the middle term. Yeah, that involves both of them. That's not be here. In order to show this, what we do, we just create a G bar here, right? Just subtract a G bar and then add a G bar. Yeah, that does not change anything. And then we can get to those terms that we want. So this, we're going to add, or we'll subtract first, G bar of x, and then we'll add G bar of x. That doesn't change anything. Yeah? And here then, now I have a square of sum of two terms, these two differences. I'm going to write out the square formula and take the expectation. Right? The first term square is minus gx square, like that. That's an expectation. Now, for the second term is a constant with respect to d, right? There's no need to take expectation, just a constant. Yeah? So just write out the square, that's it. Right? Minus f square. Yeah? Right? So a constant. And then plus the cross terms, 2 times expectation of the product. Yeah? So gd of x minus g bar of x, and then multiply the other term. But the second term is a constant, so I can pull it outside of the expectation, right? So just slightly quicker, jumping a small step. Yeah, right? It's a constant, take it outside of expectation. Why do you want to take it outside? What is this expectation? What is this equal to? What is the definition of G bar? It's just the expected value of GD, right? So when you take this expectation, you get a big fat 0. Yeah? Okay. So it's simply 0. Oops. Come on. 0 right here. Yeah. What about this one? Well, this one now is just simply the variance, right? By definition. This var of x. What is this guy? This guy is simply the bias. Yeah? So because the cross term goes to 0, therefore clearly E of x equals to the sum of bias plus variance. Okay? It's a very quick proof, right? Nothing tricky there. Yeah? So easily we can see that the average test error equals to bias plus variance. Now this only works when your error is a square error, yeah, for square. So it only works for regression, yeah, does not work for classification. So now we know that the test error is equal to the sum of these two. Then ideally we want both of them to be small, right? We want both the bias and the variance to be small. That way we have a small out of sample error. Yeah? So, but do we have that though? Okay? It turns out that no, we don't have that. We cannot make both of them small at the same time in general. Okay? So there's a trade-off between those two, variance and bias and variance. Okay? So to see this, let's first note, let's try to understand what the bias is. Yeah? The bias is right, the average, on average, how good your learning is, right? On average, how good is the best hypothesis that you can choose, how good it is. So how well your learning model, basically you have to choose the best one out of through training, but this hypothesis comes from your hypothesis set. Yeah? What is the best hypothesis in each, yeah, in this learning model, the set of hypotheses you have. approximate the target function. Right? On average. Yeah. This is, of course, is again average over the realizations of the training data set that you're given. Yeah, right? Basically, how good your learning model is. Is it a linear model, quadratic model, neural network? How good it is, in general. Yeah, knowing that you're going to get random training data points, but you just look at average. Yeah. Then the variance is what? The variance is the variance how your final hypothesis changes corresponding to the changes in your training data points, right? Yeah, that's the randomness. The training data set is the randomness. So this tells you how sensitive is your final hypothesis with respect to your training data points. Yeah? How sensitive is this best kind of out of your training? Yeah? Your learning algorithm is best. With respect to D, yeah? That's what the variance means, right? Yeah. And then turns out that the sum of these two give you the test error. So let's draw a picture of this. I want to draw here. That's a special thing here. This is I want to draw the labels for a single data point. Okay, the possible labels of a single data point. So there are many possible labels, depending on what hypothesis you have in the hypothesis set. So I want this rectangle to represent the space of predicted labels for a single given x. Okay, so suppose I have a h that's like this, yeah. Then there are these different data points here. Right. Like that, yeah. So say this point might be corresponding to h1 of x, right? And then this point, say, corresponds to h2 of x. Yeah, this is h2 of x. Like that, right? So again, these points are not our training data points, right? These points are their labels, yeah? They are possible labels for the same data point. Okay, is everyone clear about the definition here? Yeah? Each dot here is a possible label for this given data point x. Yeah? Okay? Because we have multiple hypotheses, so we have multiple data points. Yeah? This circle will represent your hypothesis set, what kind of labels it can generate. Yes?
When you say the sum of all points, is that like, for example, if this is a regression, it could be like an infinite number.
Yeah. This will be, in general, a d-dimensional, well, not d, some real space, multi-dimensional space.
Well, it's like, but if it's like binary classification, right? Would we only have like 2 points even if we have like 20 hypotheses or something like that?
Yeah, that's right. Yeah, if it's a binary, then you have 2 to the whatever power, 2 to the nth power possible points for the decision no, I'm sorry. For binary decision, then you can only have 2 possible values for the label, +1, -1. Then I will have only 2 points, no matter which.
So that's just like the numerical output rather than saying mapping it from each hypothesis.
Yeah, each one of x gives you a prediction for this x, right? So that's the number. That's the y, right? The y1. So basically, this is y1, y2, y3, y4. Oh, no. What I'm talking about? No, y1, y2, we use yn, which is the data points. No, this one's just simply h1 of x, h2 of x. There's no other symbol that we use for this one. The big H contains h1, h2, all the way to hm. For the same data point x, therefore we have h1x, h2x, all the way to hmx. We have that many numbers. I'm just putting all of these numbers here in this space.
Okay. And so, like, again, like for the binary classification, like you can only have like +1.
That's right, only two possible points. And I would not even draw in a two-dimensional graph in that case, right? It's only on a one-dimensional line. Here, this is in general that the label can be multi-dimensional labels. Yeah. Is this clear at all what we're doing here? Yeah, again, these are not data points as we are more used to seeing in the past, right? These are not data points. This is for a single data point, the labels, possible labels out of your hypothesis. And then here we're going to have maybe the true labels here. Yeah, f of x is right here. Okay. And then you train your model. Yeah, this is given your model. You train it. Maybe at the end, you have this G bar over here. Let me use a different color. Maybe G bar of x is here. Yeah, it tends to be maybe closer to f than the average of the hypothesis because you're training it. So this will be your bias, right? By definition, the distance will be bias. Now, if I do the same thing for a larger hypothesis set, what would that look? So if I have a larger hypothesis set that maybe even includes f of x, right? So I'm going to have more hypotheses around. Clearly, during training, you have more chances to get close to f, right? Yeah. So therefore, on average, you will expect that the f bar, the g bar, to be better. Yeah. Maybe g bar now is over here. Yeah, this is your g bar. Okay. And this will be the bias. So is it convincing that in general, when you have a larger H, your G bar tends to be smaller, the bias tends to be smaller? Yeah, because you have more chance to optimize, get close to F, right? Yeah, does this make sense? So you will have to see this, so we have to use this space of the labels to see it, right? Yeah, we are now closer to the true label of this single data point X. Yes? Yeah, but that would be a different hypothesis. Yeah. So yeah, but usually we don't know, which hypothesis set is close to F. But usually we only know this hypothesis is smaller set, another hypothesis set is bigger, linear versus quadratic. Yeah. So so that's what order we're talking about. For a smaller hypothesis versus a bigger hypothesis set. So we can see that if we are smaller or just small h, we get a large or larger bias. Yeah, and if we have a large h, in general we get a small bias. Right? So everyone agree with this, right? Again, our goal is to have both bias and variance to be small. So this one says, well, a large h will be good, right? But what about the variance? Remember, the variance is the sensitivity of this best hypothesis with respect to some random quantity, right? A larger h, of course, will give you more randomness. Yeah. So unfortunately, when you have a large h, even though your bias is smaller, you get a larger variance. Yeah. And whereas small h gives you a small variance. Yeah. Therefore, there is a trade-off between bias and variance. When you try to, again, our objective is to minimize the test error, right? Minimize this E of x, which is sum of those two. But then it turns out that I don't have a perfect h in one direction or the other. Yeah, the perfect h will be somewhere in the middle, not too small, not too large, just as what you would expect. Yeah, and that's what we observe in classification as well through the E in and delta G trade-off analysis. Yeah, so here that our trade-off is between the bias and variance. So bias. Variance trade-off. And this is unique to the square difference, square error difference. The square error definition of the square error function. Yeah. Okay. Any questions at this point? Now this is a per sample error, okay? Per sample error E of x. In general, we still want to know the test error defined as an average of this per sample error, right? So we just go one more step, take the expectation of that. It still works. Yeah. So we can further average. Further averaging over this x, which is out of P of x. Right? So recall that our normal definition of the test error, E out, of this final hypothesis GD, is an expectation over x, right? Of this GD of x minus f of x. So previously we say, well, if we are given a training data set D, then the E out is a deterministic thing, right? Whereas E in is still random, even given D. Yeah? But now we have one more layer on top of that. We see that when your D is random, then this clearly, even E out itself is also random, right? Yeah. So that's one additional layer on top of that. So we have to note that this thing, even E out, is random. Yeah, since D is random. Okay. So therefore, we have to define an average over D. So we're going to define E out bar as the expectation over D of this E out of G of D. Yeah, this would be our ultimate measurement of the test error, right? Yeah. This would be if E out bar is low, that means that regardless of the randomness of the training that we get, on average, we do well in learning, right? So how do we find this? So ED of this E out itself is also E of x. So we have two layers of expectation, yeah? But expectation is linear operator, yeah? So we can swap the order of the expectations as long as they converge. But that's usually is true. So we get ED, EX, and then ED of this GD of x. Like that. Yeah. But you recognize what's inside the E of x? What is this ED of this one? This is just our per sample error, right? This is just E of x. You see? This is our per sample error, as we defined at the beginning. Yeah? So, and we know that this is equal to bias plus variance, right? So this is equal to bias x plus Ex of the variance of x. Yeah? And well, we can just relabel this as bias bar plus variance bar. Yeah? So therefore, after we take the expectation over the test sample, we still have the test error equals to the bias plus variance. Yeah? So therefore, the bias plus variance trade-off still holds, even after expectation. Okay? So we continue the previous example that we did a bit in a bit rush earlier this week. Let me repeat. D equals to 1. Okay. It's so we have an x that's between the space of this learning is between -1 and 1. We have an unknown target function, which is y is equal to sine pi of x, right? That's what we need to learn. But then in this very simple toy example, we won't have one data point for training, yeah? So that we can do some simple analysis by paper and pencil. U and V like that, right? Yeah. Where the location of the data is uniform. Location of data point is uniform between -1 and 1. And then the label of this data point, of course, is simply labeled by this target function. Yeah, right? And we consider very simple, again, this is a very toy example, right? Set of hypotheses that are all constant. Set of, so this is even simpler than linear hypothesis, right? This is constant hypothesis. In other words, every single of these hypotheses is mapped to a constant C, no matter what x is. Yeah? So, the setting clear? And last time we have already said that, well, in that case, what would be the final hypothesis for your learning algorithm? This learning algorithm is very simple, right? Yeah? Only have one data point. What choice do you have? You know, we just say whatever x is, the label is v, right? That's the only thing we get, u and v, right? Yeah. Later we're going to extend this into the case where we have two data points in our training sample. Yeah. What should be the final hypothesis? What would be the best final hypothesis? Yeah. So recall from last time that we already calculated something that the average of this final hypothesis turns out to be 0. Yeah. That means what? You know, let me draw the picture first. Yeah. You know, I'll write it down. I'll write this down, and then I'll draw the picture. Bias we saw from last time. It's a sine square pi of x. The variance is a half. Yeah. And then overall, we have this picture. -1, 1. The dotted line is the target function that we want to learn. But we are only given one sample point to learn about this entire target function, which is very hard to learn, right? But then this point is what we're given, right? U and V. But as a toy example, this is good enough. Yeah. Given the single point, we have to learn this sign. Clearly, not very easy. Nothing much we can do. So we say, well, for constant hypothesis, then this will be our best guess, yeah, the best estimate for the target function, right? The final hypothesis. Given one data point, really that's the best you can do, yeah? Okay. And now our interest, of course, is what happens doing testing, right? If I give you a test data point x, yeah, where is the error? Well, your estimated label for x is still g of x, which is still v, right? Still the same number, v. But then the true value is f of x. Yeah. So the test error with respect to this data point will be between these two red dots, right? It's right there. That's our test error. And this GD is a random thing. Why? Because it depends on where U is. Yeah, this training data point is random chosen, right? Between -1 and 1. U can be here, U can be there. So you can imagine this GD fluctuates, you know, as a horizontal line all the time, but then could be higher, could be lower. Yeah? G bar equals 0 means what? The average all of these horizontal lines is right here on the x-axis. Yeah, the average of them, which makes sense. Yeah, it is. Okay. So since we have that, then we can find the if we want to find the test error, the average test error, then we have to find the average of bias and the average of variance, right? So we have to, bias is the expectation over x of the bias of x, right, which is a sine square of pi x. Yeah. This, as we have looked at quickly last time, is equal to, this is the expectation of a function of a random variable x, right? So to take the expectation of a function random variable, you put the PDF of the random variable here, right? The PDF is half, right? Because x is a uniform random variable between -1 and 1, right, for the test data. Yeah, and then for the sine square, we make it 1 minus half of 1 minus cosine 2 times pi x. Yeah, d of x. And then we know that the integration of cosine 2 pi x is 0 because between -1 and 1, you have 2 cycles, yeah, 2 periods of this sinusoid. So the integration is 0. Therefore, we only have left with the remaining constants. Turns out to be half. Okay. What is the average variance? Well, it's EX of this one turns out to be just half. Therefore, you know, there's no change. Yeah, that's not dependent on x. Given this, we know that the average test error is simply half plus half. Yeah, equal to 1. Okay. Everyone okay? So let's take a look at the case of having 2 data points. If everyone is okay with the case with a single data point. Everyone doing okay so far? Any questions at all? Is this? It requires some probabilistic thinking. Yeah, it may not be familiar to everyone. We're going to use the previous example, yeah, but and we have 2 data points. So in other words, D. Let's say we have U1, V1, and then U2, V2. Yeah, 2 data points. So I'm going to just copy and paste that figure over, I think. You know, easier to just draw again. -1, 1. The sinusoid target function that we don't know, that we need to learn. But now we have 2 data points to learn from. Let's say first data point is here, second data point is there. Yeah, so this is U1, and of course this is V1, and then U2, V2, like that. Okay, so we have 2 data points to learn about this sinusoid. Still not very good, clearly, right? But it's better than having just 1 point. Yeah. So, so that we can have a toy example to at least do some calculation, right? Obviously, to learn this sinusoid, you need a lot more points than 2, right? Ideally, maybe 10 points. Then it's probably good, pretty good that you can see the shape. But we cannot easily solve that problem by hand. When you have 2 points like that, what would be the best GD? The best hypothesis, what do you think? Still constant hypothesis, right? What is it? Come on, easy, right? Yeah, the average between those 2 points, right in between, yeah? What else can we do? We have these 2 points, 2 values. We have to find a constant, then the best constant will be right between them, yeah? So this GD of x equal to V1 plus V2 over 2, right? So still a constant model, right? We have no choice. And again, we want to see for this x how good it is, right? Say the error, yeah, in general, how big it is. Is it bigger or smaller? Yeah, when we have more data points to learn from. Let's see. So what is the average hypothesis? Of course, it's ED of GD by definition. So this is ED. Now there are 2 points, right? So U1, U2. They are both randomly chosen independently. Yeah. Now this is V1 plus V2 over 2, right? Like that. And so this is simply half of E U1, U2. V1 plus V2. V1 is simply sine of pi U1. And then the other one is pi U2. Yeah? Right? Now, because U1 and U2, they are chosen independently of each other, right? We can break up this expectation into 2 parts. And the first part has something to do with U2. The second part has something to do with U1, right? So I can rewrite the expectation. I can simplify this. To the first term, it's only expectation over U1 of sine pi U1, right? The second one only has to do with U2, so expectation over U2, sine of pi U2. Yeah, they have to be independent. Independence. So this independence and also identical distribution. This is the structure that we need for learning, right? At least this type of analysis to work, right? And that's what we have assumed, anyways. Yeah? So therefore, well, we know clearly see that each one of these expectations is 0, yeah? Because it's a sign. If you write out the integration just like what we have seen before, you are just integrating a anti-symmetric function between -1 and 1, so they all go to 0 no matter what. So this is 0. Yeah, turns out that the average hypothesis is still 0. Yeah. So therefore, the bias is still the same. Bias x is still 0 minus f of x equals to fx squared, so sine square of pi of x. Right? Yeah. And the average bias is still the same as before, sine square pi of x. Yeah, as we have solved earlier, this is from the previous analysis, we get half, right? This expectation gives you half. Yeah. The variance, again, is ED, by definition is ED, GD of x minus G bar of x. Yeah? Right? How random this GD can be, right? And again, this D I can write it as U1, U2, and G bar is 0, so this is V1 plus V2 half, that's our GD. Square that, that's the expectation that we have to find, right? Once you have this, then the rest will be simply algebra, yeah? So this is 1/4 because of the square. U1, U2. Here you have U1 square plus U2 square plus 2 U1 V1. I'm sorry, V1 square plus V2 square plus 2e1 v2. So this is a sine square pi u1 plus sine square pi u2 plus 2 times sine pi u1 times sine pi u2, right? And the first term has nothing to do with u2, so we have just eu1 of sine squared pi u1. We know this is half from previous, yeah? So the first one is half. Second one, by symmetry, is also half. How about the third one? What is the expected value of this guy? Well, these two are independent, right? So expectation of the product equals product of the expectations. And each expectation here we know is 0 from our previous analysis. So this thing is just big fat 0. So like that. Yeah? So therefore, the variance is a quarter. Remember what happens to the previous one? When we have only a single data point, the variance was half, right? So we actually reduce the variance. And the average variance, of course, is still 1/4. Yeah? That means our test error is equal to the bias half plus variance a quarter equals 3/4. Smaller than before, right? Remember what was before? E out was 1, right? Before the test error was 1. Now we reduce by 25%. And this is because we have more data points to train. We have more knowledge about this curve, right? Instead of just 1 point. Yeah? So this is because we have larger n. Yeah? More knowledge. So we reduced variance. In this particular case, I probably should say here, yeah. In this particular case, the bias does not change when we increase n. But that's not always true. Okay? In other examples, you see that changing n will also change the bias. Yeah. But overall, larger n, in general, you will reduce the variance. Because you fit to the more data points give you less choice to choose the best hypothesis, basically. Yeah, more data points limits how you can choose the best hypothesis. So overall, you give you smaller variance. Kind of intuitive explanation. Okay? So in general, it turns out this is true. Do I have space for this? Yeah, I'm going to put it here. In general, beyond this example, we can plot figures like this. And I'm going to draw the bias here. Draw it higher, okay, because I'm going to have to draw something lower. Leave some space for the place that's lower. So suppose this is the bias as n increases. And this is the idealized case. Yeah? In general, the bias will also change a little bit. Yeah? Although not as pronounced as the variance. Yeah? But the variance will change. The variance will substantially decrease as you increase the number of data points in the training. Yeah? So let me say this is the variance, the difference here. So this overall is E out. Okay? So this is the variance. I want to write it on the right hand side because I want to save the left hand side to draw something else. Yeah. Suppose this is the bias and variance trade-off. That's not trade-off yet, I'm sorry. This is just the behavior of the variance as you have larger and larger training data set. Yeah. Now suppose I have a bigger hypothesis than the blue one. Where do you think the bias is? So suppose this is for one hypothesis set, so one learning model, I don't know, linear model or constant model. I have another more sophisticated learning model. Okay, where would the bias and the EL curve be? What do you think? Say a bigger H. Remember our kind of pictorial, somewhat hand-waving argument here that says larger H will give you smaller bias, but larger variance. Yeah? So if I have a larger H, my bias will be lower, maybe here, right? So this is a more complex H. Above is a simpler. I want to avoid using bigger or smaller because you have seen before, right? Whether it's complex or not really depends on the, say, something like the VC dimension. Even if infinitely large H does not mean that it is a complex H. Right? Okay. How about the variance? Yeah, the variance will be bigger, right? So let's say the variance for this red one is like that. Here, this is the variance for the same point. Yeah, same. Then that means, I'm going to draw the line first. It might look something like this. Yeah, so this would be the. I want to draw this flatter. Yeah. This is the E out for the more complex model, right? The variance here will always be bigger than the blue one, right? But then your bias is smaller. That means that eventually, as you have more and more data points, you converge to a lower point, converge to a lower error. Yeah? However, if you don't have enough data points, it may happen here that the red line is above, you have higher error. Yeah? Make sense? Yeah? So this is what this figure shows, what it's trying to illustrate. Yeah? That point. So let me add another, continue. So we'll have more samples, give you more complex. H will be better, right? Okay. So again, drawing this connection between the number of sample points you have and the complexity of the model that you use. We have seen similar kind of analysis before, right? When we have the N and M, or the growth function, MH, when we do classification. Yeah? So we have similar conclusions. If you have more data points for training, then you can afford to have a more complex model. Here. Thank you. All right, let's start again. So the last topic of the semester is validation. We're going to spend 3 lectures on this. Now, but because of our final exam is pretty early, today's lecture will be the only one that will be included in the coverage of the final exam. Okay? So whatever we talk about next week won't be in the final exam, because you won't have a tutorial on those materials first. Right? So there will be no homework or tutorial for the stuff next week, but there will still be one more homework that will be assigned later today by the TA, which will include some of this stuff today. Yeah? And that will be in the final exam. So the general setup, again, we have the data set. Like this. And then xn, of course, is a joint IID from a distribution P of x. And yn is obtained from a target function. Yeah. So of course, in general, that we have been doing this. You send the data points, the training data, into a learning algorithm. And the learning algorithm gives you a final hypothesis G. Yeah. And then we can talk about the training error, which is, of course, our E in. So now we're going to assume a general error function, right? That doesn't have to be an indicator function for classification, or doesn't have to be a square error for this general E. Yeah? And this analysis will work for any E. Yeah? And then test error. E out of G, which is a expectation of this E, of course, over the test sample X that you can be given. Yeah. And as we know very well by now, there is no exact mapping between the training error and the test error, right? E in can, this keeps showing up. This E in goes down, and the x-axis can be anything, really. It can be the number of iterations of your algorithm, can be the complexity of your hypothesis set, or the learning model, and so on, right? So this is something, let's say, yeah? And then the E out, we tend to go like this, right? After a while, it goes in opposite direction. So this something can be when to stop your iteration, for example. Yeah. Oh boy, maybe we need to restart the program. But anyway. Which learning model? Okay, I'm going to restart. Sorry about that. mouse disappears. Hopefully that fixes it. So this could be the which learning model. Basically, the learning model complexity. The more complex is the learning model, then your E in is smaller. And you can also use this kind of curves to indicate, well, the impact of hyperparameter. Yeah. So of course now the question is, during training like that, since we won't have information of E in, we don't know when to start, right? But our ultimate objective is E out. Ultimately, we want to get this point. The question is, how do we know from the training itself? Yeah, that's our problem. We want to estimate E out using only our training data, which is the only thing we have, right? Estimate E out of G from training data. Yeah. We have no other choice. Of course, the solution you have seen already in your training, in your programming assignments, we do validation. Yeah, we use a validation data set. But the validation data set does not come out of nowhere, right? We only have the training data set. So the only way you can have a validation data set is to split it away from your training data set. Yeah? So we have this D, we have to split it into D train and D val, right, for validation. So if you have originally have n samples and you want to have k samples for validation, then that means your training, you only have n minus k samples left. Right? And you know this very well because you have done this quite a few times in your programming assignment, right? And during training, you instead of using a D to send it in like before, when you use the entire data set, now you don't have the entire D to use. You only get D train to use to do the training. Yeah, you send D train into your learning algorithm. And then you don't get G, you get something called G minus, let's say, yeah? A bit less than the original G because you have few data points. But now you get a chance to do validation. And you can check the validation error, which is we denoted by eval for this G minus. Right? It is, of course, 1 over k, it's the average. Right? So xn is in the validation set of this error. Yeah? So it is the average error over the validation set. Right? Yeah? This is very clear, right? This is what you have done already. Should be very familiar to you. Yeah? We're just writing it down more formally, mathematically, that's all, right? Yeah? Our hope, of course, is that this validation works. Yeah? What does it mean? What does it mean that this validation works? Well, this validation gives you a good estimation for the test error, right? Estimation error should be close to the test error. So we want eval G minus to be approximately equal to E out of G minus. But that's not quite enough because in reality, we are supposed to get E out of G, right? Yeah, but G is the one that you, if you are using the entire data set to train. Yeah. The second point here says that, well, basically, I don't want my validation to suffer, to make our training suffer too much. Yeah. Under one condition, are these two approximately the same? In other words, G minus and G, they are approximately the same. Under what conditions? Same data points, yeah, but then we don't have, so your k has to be small, right? You don't split too many data points for validation. So this will be when k, if k is small. Yeah, that's clear. To have the second part to be good. Everyone okay with this idea? Yeah? Yeah? Yes? G minus is this one, using your training data set. Remember G at the beginning? That's the G, right? Our full data set. So basically, here, the second part means that we don't want to pay a penalty too much. We don't want to pay too much penalty for using validation. Yeah? Okay. So therefore, if k is small, if you don't throw away too many data points for set it aside for validation, then we don't pay too much penalty. Right? Yeah? So second one is clear. The question then is the first one. Yeah? Is the validation error really approximately equal to the test error? Yeah? Is it going to be a good estimation for test error? Again, test error we don't know, right? We don't have any information about test error. Yeah? We can only observe the validation error. Our hope is that this validation error is a good estimation for the test error. Okay? So how do we know that? So it requires some mathematical analysis. Fortunately, this mathematical analysis is very similar to what we have already done for the case of generalization. Okay? The reason being, G minus, this hypothesis was picked out of the training data set, right? And the training data set is different from the validation data set. Yeah? So G minus is independent of the validation data set. Okay? So that is a very important observation to allow analysis to work. G minus is picked independent of the training data set. I'm sorry, validation data set. Okay. So this is very similar to what we discussed before when we talk about generalization error. Remember the difference between E in and E out? Yeah? We have two versions, right? The first version is E in of H for any generally chosen H. That's independent of the data set. That one is much easier. Yeah? And then we have another version with E in of G, where G depends on the data set. That one is much harder to analyze, right? We have to do a lot more steps. Yeah? So here, this is independent, so we have an easier time, yeah, to show that this eval is a good estimator for E out. Okay? So let's look at the properties of this eval. First of all, we observe that eval, of course, it is a average of random quantities. Right? Yeah? It's random because xn is randomly given to you from the training data, from the original D. So yeah. Whereas the it is supposed to be estimation of or estimate of E out of G minus, right? That's what we are hoping to do. It's very similar to what we have if you compare E in, E out. Remember we defined it Vn, right? Equals to E in of H, where H is independent of the data set. Yeah. That Vn is also average over the sample points. Yeah. And then the E out is the same, it's a mu, right? Well, defined previously we just call this mu, we say mu is actually E out of H. I'm just trying to draw a connection with the kind of analysis that we have already seen before. Yeah? And the claim is very similar analysis. Yeah? We want to show that, previously we showed that Vn is a good estimate of mu, right? Yeah? In particular, we showed that Vn is an unbiased and consistent estimate of mu. Okay? We're going to show the same thing for this validation error. Turns out the validation error is also an unbiased and consistent estimate of the test error. So to show that it is unbiased, we have to say, well, what is the expectation? The expectation is over the randomness or the validation set that you get. Yeah. So this is eval G minus, right? And I'll just claim that this is equal to E out, okay? So therefore, this means that it is an unbiased estimator. How do we prove that this is true? Yeah? How do we prove that the expectation of the validation error is equal to the test error? So the left-hand side is equal to expectation over the validation data set. Just write down the formula for the validation error. Yeah? It's the average over the k samples you have. Xn is in this D val. And then E of G minus Xn Yn, like that. And it's an expectation, just move it inside. Yes? V and mu, what we have before, when we do the generalization analysis, E in and E out. We say that E in is a good estimate of E out. We did this 2 weeks ago. Yeah, pretty much that over there. But over there, yeah, that's exactly Hofting. Yeah, in fact, we can see a Hofting here as well. Yeah. The only difference is that here, this E is general, right? Previously, for the Hofting one, we only consider binary. Yeah, so it's a sequence of Bernoulli random variables. Here, this E is a general random variable. That's all. But this analysis still holds because I can put this expectation inside the sum, right? 1 over k, sum En over the validation set is expectation over the validation set's randomness, E of G minus, like that, right? Yeah. Now comes the important part. If you look at this Xn, it's very important to note that this G minus does not depend on D valve itself. Yeah? G minus is obtained from the training data set, right? It is independent of the validation data set. That's very important. So that we can treat this G minus as just a constant function applied on this random Xn. Yeah? Otherwise, we will not be able to do this next step anymore. Yeah? So this, I can change the expectation to only an expectation over Xn, right? Because this function does not depend on the other data points. Yeah? So it's very important that your validation data set is completely separated from the training data set. Yeah? Otherwise, you will not have this nice property of being unbiased and consistency in later. Yeah? So that's an important point. So this is independence. Yeah. Yeah. In fact, next week, we're going to look at another validation scheme called cross-validation. Supposed to be more efficient, but then that one does not give you this independence. So we cannot do any kind of this analysis at all. Only hand waving, say, okay, it works. Okay, we will see next time. Yeah. So xn is in d of d val. Once you have this, then this one is simply the same as the test error, right? Because they have the same distribution. The data points have the same distribution between test data or the validation data. Yeah, so same as E out. Therefore, this thing is equals to E out of G minus. Yeah, everyone okay? Yeah. So we have shown that the validation error is an unbiased estimate of the test error. Consistency, then we have to look at the variance. Right? We have to show that the variance of this validation error is 1 over k. Turns out to be equal to 1 over k of this variance of the, in general, g minus of x and y. That means that as this thing goes to 0, as k goes to infinity. Yeah? So therefore, this is what we call consistent estimate. Right? If you have enough sample points, then you get exactly the right result. Yeah. So how do we prove this? Pretty much the same way as we proved the E in being consistent as before. So the left-hand side is the variance of 1 over k, again, xn is in validation set, E of g minus xn, like that, right? It's the variance of this average, so we can take 1 over k out, so we have to square that. And then you have, again, because of the independence inside, the variance of the sum equals the sum of the variances. Without that independence, you will not have that. You will not have this next step as well. Variance of E g minus xn yn. But all of these data points, they have identical distribution. So this variance inside, they're all the same. Yeah. So there are altogether k of them coming together. Yeah. That k cancels out with one of these k's. So therefore, we get 1 over k, and then the variance of any general data point x. And that's exactly the result that we wanted. That's the right-hand side, right? Okay, so that's easy. Everyone okay so far? So we have seen this before, right? Just previously, this E was a Bernoulli random variable, that's all, right? So it turns out that even it's not a Bernoulli random variable, this still works. Finally, if it is a binary classification or general classification that you have a indicator function as the error, we have the Hoeffding bound. So for classification, yeah, this E is going to be an indicator function, right? So for all of the data points inside the validation set, you have a bunch of IID Bernoulli random variables. IID Bernoulli. Right? Yeah. And because of that, then we can let's say this tells us that we can use the Hoeffding bound. This says that for any delta, I'm going to write down the final one, yeah? Skipping the epsilon stage. With probability greater than or equal to 1 minus delta E out G minus, it's upper bounded by eval of G minus plus square root of 1 over, previously we have over 2m, when we use the Hoeffding bound. Now we only have k validation points, so we use k there, that's all. Everything else is the same. Yeah, exactly the same as before. Yeah. Okay. Nothing new here, right? Any questions so far? Yes? Yes?
What is it saying and why is it important?
Oh, it's consistent. That means that the variant, when the random variable, the variance goes to 0, that means the random variable converges to its own mean value. Right? Imagine a random variable. The variance represents how random the random variable is. If the variance is 0, that means the random variable is not random at all. It just equals to its own mean value. Yeah? And the mean value, because of unbiasedness, is equal to E out. Right? So that's good. Yeah? It converges to E out. And then more precisely, we can use the Hoeffding bound to tell you how fast it can converge to that E out, right? If k is large, yeah, then it converges. And then the speed of convergence is on the order of 1 over square root of k. So this is for Hoeffding bound for the binary case, and for the classification case. In general, this still works, even if it's not classification. Yeah. So in general, we don't have that exact formula, but we have the same scaling. This one is upper bounded by E validation plus something a big O order of, well, let me just write 1 over square root of k, like that. Okay? And this is just given without proof, okay? So the idea is that now this one, of course, simply converges to eval G minus as k goes to infinity. Yeah? So therefore, the validation error can be as close to the test error as you want, right? These two can coincide if you have k large enough. But what is the problem with this? So you say, okay, then I just make k very large, right? Then my validation error is exactly the test error, then I'm done, right? No problem. So what is wrong with this? Yeah. Yeah, because we have to have both sides as well, right? The second one wants k to be small. The first one wants k to be large. So there's a trade-off there again. Yeah, there's no free lunch in machine learning, or well, in life in general. There's no free lunch, right? So you always have made trade-off. You have to give up something to gain something. So what do you do? In general, then you have to pick the right k given your data set. And as you have seen in your program assignment, in general, we pick 20% of our data points for validation. And that is our general rule of thumb. No theory behind that. It's just a general rule of thumb. We're going to use k approximately equal to n divided by 5. Yeah? 20% of your data point for validation, and then 80% of your data points for training. People observe that this is usually give the best test result. Yeah. So next, let's take a look at one particular specific example of validation, which is use of validation to select the right learning model to use. Yeah. So we have model selection by validation. The idea is very simple. You have a problem that you can choose all these different kinds of models, right? Linear model, quadratic model, and so on. Given this data set, you have to select the best model from the given hypothesis set, or candidate H1, H2, HM. Yeah, for example, HI can be the ith order polynomial, for example, right? Yeah, linear, quadratic. Or it could be corresponding to a hyperparameter lambda equals some kind of AI value. Yeah. The solution, of course, is simple now that you know it's use validation, right? So step one, step zero is you break up your data D into two parts, D train and D val. And then step one, you will train each model DHM on the training data set. Yeah. To output, let's say, hypothesis GM bar. Yeah. Step two, now you check whether these are good hypotheses, right? So you check by using the validation data points, using dval. Compute the validation error for each one of these guys. GM minus, for each M. Right? And of course, then after that, you select the best one among these. The minimum one will be the best one, right? So the best model, HM star, where M star, of course, is the M that gives you the minimum validation error, minimum among all M's. Right? I mean, all of this seems obvious so far, right? Nothing tricky. That's anyone would imagine that's what you should do. Yeah, when you say, let's do validation. Yeah. This is for the hyperparameter. Remember when we do regularization, for example, right? You have a lambda, right? Some whatever parameter that you want to set. You could choose it to be 10, could be 1, could be 0.1. Which one to use, right? So that's AI value, are those different values that you want to choose from. You can view that as a different model if you want, right? Different hypothesis set. But usually we don't just stop here. We don't just say we have the best M star already, and then the GM star minus. We say we do one more step to retrain the model. Yeah, basically we want to do better. To do better than simply using GM star minus. Yeah, we're going to use the complete data set to retrain this M star model. Train HM star. And then we output that one. Yeah. Output final hypothesis. GM star. Okay, instead of GM star minus, we output GM star. Why not, right? Since we already know that this is a good one to use. Yes?
But what if, like, once we use the full data set, we converge to something
That's a good point. But in general, when you use more data points, you get better results. Right? Remember our analysis from last lecture? N larger, you actually get a lower bias. Right? Yes.
But when you train an entire data set, don't you need like more iterations to train all of the ones?
That's true. Yeah. That's assuming that you can handle just 20% more data points. Yeah.
So you just do 20% more iterations?
Yeah. For example. Yeah. So there's a picture on this. I want to draw it because it's a nice picture from the textbook. And then later, next time this one will remind us what we do with the model selection. Yeah. So we have a d-val here. This, of course, comes from D. And I draw some lines here that will intersect with the models, H1, H2, to HM, like that. So this each model is trained using the D-train and then goes to d-val to get the validation error, right? This eval G2 of minus, this eval GM minus, right? Among these validation errors, you pick the best one, HM star, and then you use the entire data set D to train this HM star to finally get GM star. Yeah, that would be the final solution you give. And D, of course, would be sent previously also sent to the above for the D train and D-val, right? Yeah. This is exactly the same figure in the textbook anyways. Yeah. So this is the model selection. Yeah. Does everyone need to go back to the previous one? Anyway, I don't have enough room to show everything. Now the question is, why do we do this? If we have all of these hypotheses already, right, inside H1, H2, H3, and so on, why not just put them all together and pick the best one among all of them, right? Another way of saying this, I can just pick the best one from H1, pick the best one from H2, and pick the best one from HM, and then I compare all of them, just whatever the best one is among these best ones. The ultimate best, I'll just pick that one. That's the hypothesis that we use. Yeah? So that's the question is, why not do that? Yeah? Why not directly train all of them? Use H, which is a combination of all hypotheses, right? Just put all of them together, pick the best one. Yeah? Yes? Yeah, why is overfitting? Any kind of mathematical reasoning for the overfitting? Okay. Yeah. No, I mean the more using the generalization analysis that we have seen so far. When you put this union together, what is changed? What kind of quantity do you get? Huh? Increase the number of hypotheses or the complexity of the overall hypothesis set. Or more precisely, if it's for classification, then you increase the VC dimension, right? So this one will have a much higher VC dimension than each one of them. Yeah. So this one will have very large, say DVC. Yeah. And therefore, very high generalization error. Okay. So you don't want to do this. Rather, you want to use validation to select the right complexity for the learning model, and then train that model only. Yeah, with that complexity, you train it. Okay, so that's what yeah.
Sorry, so when you say take the you like we run all the models and then take the average answer?
No, not the average. Pick the best one among them, right? Because you put all these hypotheses together, and then find the best hypothesis among all of them, right?
Like based on what?
Oh, any kind of training that we have done, our learning algorithm, to train a model, right? You just optimize, find the best point.
Are we already picking the best one up there?
No, this is different. This is different from picking the best one. Remember, this one we have to use validation, right? This is the best validation error. But when you do this, that means that you pick the best E in, right? You don't do this one. There's no validation here, right?
Oh, okay. So just
Yeah.
best
Yeah. But the question is, does this really work? Does it really work well, I guess I should say. Yeah. So that requires some more careful mathematical analysis. Okay? And it turns out that the analysis is not so trivial because now we introduce some dependency in our validation error. Because this GM star or GM star minus, even that one is not independent of the validation anymore, right? Now it depends on the validation data points. So our analysis will be quite a bit more complicated, and we're going to do that next time, okay, next week. And after that, so first of all, we look at the mathematical analysis of model selection using validation. And then we look at a new validation method called cross-validation, which allows you almost like having your cake and eat it, because you're not separating the training data and the validation data. Yeah. Although that one there isn't a lot of mathematical guarantee because it's very hard to analyze that case. But in general, it works better. Yeah. In practice, that one is actually quite a lot more powerful. Okay. But those are not in the final exam. But I found those are very interesting. Techniques, yeah. So I hope that you all come back next time. Yes. Oh, just because you have more hypotheses, right? Just it's more complex model now. Yeah.
I thought DVC was only for binary data.
Yeah. But this is kind of rough idea. I mean, just if this is classification, then you can talk about DVC. Okay, again, no class on Monday, so enjoy the eclipse, and then I'll see you all next Thursday, yeah?